Okay, we're going to talk about the atomic structure, and we're going to start learning how to draw Bohr models. So on your next available page in your journal, and I'm going to do this side just because it's easier for me, you need your journal, something to write with, and you need a periodic table. So you need to make sure you have that. Okay, so the title, Atomic Structure. Okay, atomic structure and Bohr models. Alright, so that's your title, and don't forget your date up there. So we're going to review a little bit. So remember from previous class that all atoms, okay, so all atoms are made of three subatomic particles. And you're going to need to know what those three subatomic particles are. Okay? So we have protons. And protons have a positive charge. So I'm going to put a plus sign. So protons are positive. You say positively positive protons. They have a mass of 1 AMU. And they are located in the nucleus. Okay, so protons are positive, they have a mass, so I can put that up there, mass of 1 AMU, and their location is in the nucleus. You have electrons. Electrons have that negative charge. They are 1/1800ths the size of a proton. Their mass is negligible, so they don't count it. So we say it has a 0 AMU, atomic mass unit, and they're located in the electron cloud. And then the last subatomic particle are the neutrons. Neutrons are neutral. So we draw a 0 with a line through it. They are neutral. They are relatively the same size as a proton, and so therefore we say they have a mass of 1 AMU, and they are also in the nucleus with the proton, so they are located in the nucleus. So these are the three subatomic particles that you are going to be responsible for. You need to know their charges. Protons are positive, electrons are negative, and neutrons have no charge. You're going to need to know the masses of them and where they are located in an atom. Okay, so because our protons and our neutrons both have a mass of 1 AMU, when you're looking or talking about the properties of an atom, the mass of an atom okay, so the mass of an atom is in the nucleus. Okay, so the mass of the atom is in the nucleus, and it also, because the mass of the atom is in the nucleus, and because of the two subatomic particles that are located in there, your protons are positive, your neutrons are neutral, the nucleus has a positive charge. Okay, so the nucleus has that positive charge. The volume of an atom is in that electron cloud. From the presentation you saw, they had the little video that showed the computer in Central Park, and if the computer was in that apartment complex, that the first energy level would be 32 blocks away in Central Park. Or you could say if you took a marble and you could go to the biggest football stadium, like the Superdome, or probably the Dallas Cowboy Stadium up there, and you go to the 50-yard line right in the middle and you put that down, and that marble represented the nucleus of an atom, the first energy level would actually show up at the very farthest seat in the stadium away from that. That is the size of an atom, why it's really small, is very immense for its size, and it is mainly empty. Okay, so remember that an atom, most of an atom is just empty space. You have that central nucleus where the protons and neutrons are, and then you have that electron cloud, and it's pretty much empty out there. Okay, so most of an atom is empty. So every one of these squares represents one atom of this particular element, and the squares on the periodic table, they represent the most stable form of that atom. Okay, so each one of these represents the most stable form of an atom of that element, and they are neutral. Okay, so atoms on the periodic table are neutral. That means they have the same number of protons as they do electrons. They are neutral. Okay? An atom's identity. You correctly identify an atom. So you correctly identify an atom by looking at the number of protons. Okay, so you correctly identify whatever atom it is that you're looking at by looking at how many protons it has in its nucleus. So when you're looking at your periodic table, no two elements on the periodic table have the same number of protons. Okay, so let's look at a square. Let me scoot this up a little bit. Okay, so let's look at a square. So let's just pick one. Let's pick neon here. Alright, so we're going to do neon. The chemical symbol is E for neon. Make sure that when you're writing these chemical symbols that the first letter is clearly a capital letter and the second letter is clearly a lowercase letter. You need to be very neat with your handwriting. And one of the things, for example, you have this and you have this. Okay, this is cobalt. This is a transition metal on the periodic table. Right here, here's cobalt. CO, like this, is carbon monoxide, which is a colorless, odorless gas that can kill you. Okay, there's a difference between cobalt and carbon monoxide. Alright, so you need to be very, very careful that when you write your atomic symbols, that second letter is clearly a lowercase letter, so it's not confused with a chemical formula. So be very careful with that. So we have neon here, and neon has an atomic number of 10, and it has atomic mass of 20.179. And so what we're going to do is we're just going to round it to a whole number. So 20.179 rounds to 20. And so from this, we are going to identify the different parts. So we know this is the atomic number, and this is the mass number or atomic mass. Okay, so remember, your atomic number is equal to the number of protons. which in turn, since these are neutral atoms, it is equal to the number of electrons. Kind of made it fit. Okay, your atomic mass is equal to, or is, it's the number of protons, so the number of protons plus your number of neutrons. Okay, so your atomic number is your number of protons, and since these are neutral, since every one of these squares on the periodic table is neutral, it also is going to give you your number of electrons. Your atomic mass, of course, is your number of protons plus however many neutrons you have in that particular atom. Okay, so this is very important. You need to remember that as we go through and look at these. All right, so let's identify how many protons, neutrons, and electrons we have in a few of these elements. So find chlorine on your periodic table. Chlorine is atomic number 17. So I'm going to put Cl, chlorine, so lowercase l. Chlorine has atomic number 17. It has atomic mass of 35.453. So 35.453 rounds to 35. Okay, so off to the side, I want you to put P for protons are positive, an E, electrons are negative, and an N, and neutrons are neutral. So we're going to determine how many of each of these that we have. So remember, our atomic number equals the number of protons. So if I have, of atomic number of 17, I have 17 protons. Remember, these are all neutral, so if I have 17 positive charges, I have 17 negative charges to balance it out. So I have 17. In order to find the neutrons, because my neutrons is my number of protons plus my number of neutrons, I have to subtract these two numbers. So I'll take my 35, which is my atomic mass, and subtract off 17. Okay, so that should be 18. And so my number of neutrons is 18. Okay, so let's try another one. Turn my page here. All right, so everybody find magnesium. So find magnesium. Magnesium is the symbol Mg. Magnesium, not to be confused with manganese. It's two different elements. So magnesium is the symbol Mg. It has an atomic number of 12, and it has an atomic mass of 24.305. So if it has a mass of 24.305, that's going to round to 24. So I'm going to put 24 here. Okay, atomic number, my atomic mass. I'm going to put my acronym: protons, electrons, neutrons. Writing them like that kind of helps you remember. It spells pen. Helps you remember it out. Remember, my atomic number is my number of protons, which I have 12. If I have 12 positive charges, I have to have 12 negative charges since it's neutral, so it is 12. In order to find my neutrons, I have to subtract my atomic mass and my atomic number, so 24 minus 12 equals 12. So my neutrons are 12. Okay, so let's do, I'm going to draw a line here. So let's find, I don't know, how about oxygen? So oxygen is a capital O. Oxygen is atomic number 8. and atomic mass of 15.999. So 15.999 is going to round to 16 because we're going to make that whole number. So I have protons, electrons, and my neutrons. So atomic number, number of protons. If I have 8 positive charges, I have 8 negative charges. I take my mass, subtract off my number. So 16 minus 8 equals 8. So I have 8 neutrons. Okay, so in these two examples, they're all exactly the same. The neutrons are not always going to be the same number as your protons and electrons, and that's fine. They don't add any charge to it because they're neutral. The only thing they do is contribute to the mass of that atom. Alright, so that's how you find protons, electrons, and neutrons. So hopefully that will help with that. Alright, so now we're going to talk about how to figure out how to draw a Bohr model. And so there's some rules that go with this that you're going to need to know. Okay, so I'm just going to divide this up a little bit, and I'm going to put a subheading of Bohr models, and then we're going to talk about that. And it has to do with this periodic table. So first thing we're going to look at is how many periods are on a periodic table. A period goes left to right, okay? And so we have 7. There are 7 periods on the periodic table that go left to right. Your lanthanide and your actinide series actually fit right here. So this whole table would split apart and they would slide up in there. They're not part of any group. Any of these transition groups are not part of any of those, but they are actually part of period 6 and 7. They put them down there, and then that way, instead of your periodic table being twice as long as it is, it's a much more compact size. So your lanthanide and actinide series are here down at the bottom. They are part of period 6 and 7. They're just not part of any of these groups. Okay, so you have 7 periods on the periodic table. So let's write this down. So the periodic table has 7 periods. Okay, and they move left to right, like you would write a sentence, left to right, end with a period. Okay, the period number, okay, so your period number, is going to tell you, or tells you, how many energy levels okay, so how many energy levels your atom has. Okay, so that's what it tells you. So when you're drawing your Bohr model, remember when we looked at those in the last set of notes, and we talked about how we're going to be drawing a Bohr model every time. And they have energy levels, and for us, we're only going to go up to 7. Now, when you get to chemistry class in high school, you'll realize that those levels are actually broken up into 7 sub-levels. But for right now, for 8th grade, we're learning the basic information, and we just need to know there can be up to 7 levels. So, period 1 only has 2 elements in it. You have hydrogen and helium. So period 1, when you were drawing it, period 1 has 1 energy level. That's all. There's 1 energy level on period 1. Okay? Period 2. Okay, so period 2 starts with lithium, beryllium, then you go across boron, carbon, nitrogen, and end up at neon here. So period 2 has 2 energy levels, and that is all. Okay, So period 3, starting at sodium, going straight across, and ending at argon, has 3 energy levels. So period 3 has 3 energy levels. Are you seeing a pattern here, I hope? So period 4, I think you can predict how many energy levels do you think period 4 has. So period 4 has 4 energy levels. Period 5 would have 5 energy levels, 6 would have 6, and 7 would have 7. So if you were drawing an atom anywhere between francium and lawrencium here, because remember lawrencium is part of period 7, it would have 7 energy levels, and it would be a massive atom that you would be drawing if you drew those. Okay, so that's how you figure out how many energy levels your atom will have, and it'll make sense hopefully here in just a few minutes. Okay, the next thing we're going to look at are our group numbers. Or maybe not. We'll come back to group numbers because we're not ready for valence electrons just yet. So we'll come back to that. Okay, so on your energy levels, there's only so many electrons that can fit on each one. And in your notes that you taped in your journal, I actually gave that to you. So in your notes that you taped in your journal, if you go here to the atoms and structure ones, and you look in the middle where it talks about electrons, electrons have that negative charge and travel in orbitals or energy levels around the nucleus and appear to form a cloud. The mass of electrons so small that it can be considered as 0 AMU. The first energy level can only hold 2 electrons. The second energy level can hold up to 8 electrons. The third energy level can hold up to 18. But for the atoms we will be doing in class, we're not going to need 18. Most of them, they're just going to have 8. The 4th, 5th, 6th energy levels can hold a varying numbers, usually in multiples of 18, and then the last level of any atom can only hold 8. There is a limit on that very, very last level of only 8 electrons. So you do have this. If you can't remember, you've got this information right in your notes, in your journal. Okay, but we're going to write it down here too. Okay, so electron configuration. So let me go back to this just so that it'll make sense. So when you're drawing your Bohr model and you have your nucleus, so I'm just going to draw an N for nucleus, okay, saying that's the nucleus. And understand that the nucleus is not a membrane-bound organelle, because when you think about a cell, you know the nucleus, it's a membrane-bound organelle. It is not. It just has your protons and your neutrons in it. Okay, it's not a membrane-bound organelle. It just has protons and neutrons. And so you have your energy levels on the outside of it. Okay, so period 1, so this would be 1 energy level, 2, 3, 4. So if you were drawing the model of any element within period 1, hydrogen or helium, you would only need 1 ring. If you were drawing anything in period 2, you would just fill up the first 2 levels. Period 3, you would only fill up the first 3. Period 4, the first 4. So depending on where your atom is located, what period it's in, is to how many of these energy levels that your atom would actually need. Okay, so that's what we're talking about when we're talking about energy levels. And understand, we use the Bohr model because it's predictable. Whereas in reality, it's the electron cloud, and these electrons could be anywhere at any given time within an energy level. Okay? So, energy levels, that's what these lines represent, these circles around nucleus represents are your energy levels. Okay, so the first energy level, can only hold 2 electrons. That's all that will fit in there. Okay, the second energy level can hold up to 8. You don't always need all 8 of them, but it can hold up to 8. The third level can hold up to 18, but remember, for most of the ones we're going to draw, we don't need all 18 of them. Okay, and then it just keeps going from there. So these are how the electrons go, and you always fill the energy level closest to the nucleus before you move up on to the next one. That's one of the rules. So when filling the electrons on here, so when filling, energy levels, so when filling these energy levels, you start with the level closest to the nucleus. Okay, you always start with the level closest to the nucleus. So let's try one. Okay, so let's look at I don't know. Let's pick one. Let's look at helium. Okay, so helium, it has an atomic number of 2. And it has an atomic mass at 4.002. That'll round to 4. Okay, so then we need to go in. We'll figure out protons have a positive charge. Remember, electrons are negative and neutrons are neutral. So my atomic number is 2. Remember, the atomic number tells you how many protons you have. So I have 2 protons. If I have 2 positive charges, I have to have 2 negative charges, so it's 2. I have atomic mass of 4, so remember, you take your mass, subtract off your atomic number, and that gives you a number of neutrons, so I have 2 neutrons. Okay, helium, if you can go across, helium is in period 1, which means it has 1 energy level, which means we only have to draw 1 ring. Okay, so I'm going to draw 1. Okay, so I have 1. The nucleus is that central portion of the atom. And so, if you remember what we wrote down, the protons and the neutrons are located in the nucleus of your atom. So you're going to take, we have 1 proton, and I'm just going to put a P with a positive charge. We have 1 proton, and I'm sorry, we have 2 protons because we're doing helium. So we have 2 protons and we have 2 neutrons. So N. So we have 2 protons and we have 2 neutrons. Our electrons are going to go on our energy level outside our nucleus. So the way I learned when I was in school, and I still do it to this day, is I draw a lowercase e with a negative sign. That's how I was taught so many years ago, and I still do it that way. Okay, so I have my 2 protons, my 2 neutrons in the nucleus, and I have my 2 electrons on the energy level on the outside of the nucleus. Okay, so now let's look at lithium. So find lithium. Lithium is the symbol Li. Notice I made sure that I was the lowercase I, so there wasn't any confusion. Lithium has an atomic number of 3. its mass is 6.941, so 6.941 will round to 7. Okay, so I have my protons, my electrons, and my neutrons. So my atomic number says I have 3 protons. If I have 3 positive, I have to have 3 negative charges. In order to find my neutrons, I take my atomic mass and I subtract my atomic number. So it would be 7 minus 3 equals 4. So I have 4 neutrons. Lithium, if you look at your periodic table, is in period 2. So since it's period 2, according to what we've already written down, period 2 has 2 energy levels. So we're going to draw 2 circles. So draw 2 circles. And it doesn't matter if they're not perfect circles, but 2 circles. So inside our nucleus, we're going to do our protons. So this time, I'm just going to do 3 circles with a plus in them. A little bit different. So my 3 circles with a plus in them, which you can't really see that well. And then I have my 3 neutrons. And I'm just going to color them in all the way. 4 neutrons, right? Okay, so my neutrons, I'll just make a little key. I colored them in, and my protons, I put a plus in them so I can tell the difference between them. I need my 3 electrons. So, according to what we wrote down, the first energy level can only hold a maximum of 2 electrons. And we always start with the level closest to the nucleus. We fill it first, and then we move out to this next level. So our first level, close to our nucleus, can only have 2. So I'm going to draw my E. And that's going to be, the first level is full. I need 3. I only have 2. So the whatever's left over is going to head on to the next level. And I only need 1 more. So now I have my 3 electrons, my 3 protons, and my 4 neutrons. And that's the Bohr model for lithium. Okay, so let's try another one, because the more we practice, the better we're going to get at them. So the next one we're going to do is sodium, which is right under lithium. Okay, so Na is sodium. It is atomic number 11, and it has a mass number of 22.990. So 22.990 is going to round to 23. Okay, so sodium has a mass number of 23. I have my protons, electrons, and neutrons. My atomic number is 11, so I have 11 protons. I have 11 electrons because it's neutral. These have to cancel each other out. In order to find my neutrons, I have to subtract my atomic mass and my atomic number. So 23 minus 11 is going to give me 12. So I have 12 neutrons. So 11 protons, 11 electrons, and 12 neutrons. Sodium is in period 3. So I need 3 energy levels. So I'm going to draw 3 circles. Okay, so 3 circles. So inside my nucleus, I'm going to put my protons and neutrons, and this is how I'm going to do it because I'm getting so many subatomic particles. I'm going to put a P positive equals 11, and my neutrons are neutral equals 12, and then that way it's not so busy in the middle and it's easier to read. So we're going to fill the level closest to the nucleus first, and there can only be 2, so we're going to put 2. Okay, so we still need 9 more. because we need 11 in all. We're going to fill the next energy level, and according to our notes, the second energy level can hold up to 8 electrons. So we're going to put our 8 electrons on the next energy level. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 on the first, 1, 2, and we have 2, 4, 6, 8 on the second, so that's 10 in all. We need one more, and that is 11. So then that will fill, that's all of our energy levels filled with the amount of electrons that we need. Okay, so now that brings me to valence electrons. We talked about valence electrons in the notes that you guys took last class period. So valence electrons are the electrons that are involved in any type of chemical bonding. Okay, so valence electrons are the electrons on the very last energy level. Okay, so that's what valence electrons are. They're the electrons on the very last energy level. Valence electrons are involved with chemical bonding, or I guess, yeah, chemical bonding. You could say chemical reactions, but chemical bonding. And there's a maximum number of valence electrons an atom can have. They can only have 8. So there can only be 8, okay, valence electrons. And I'm just going to put a VE for valence electrons. There can only be 8 of them. Now understand when I say that there are some elements, especially in the transition metals, that don't follow that rule. But for all the ones we're going to be doing, there will only be 8 valence electrons. Okay, so now back to our periodic table. And it's going to tell you how many valence electrons are in each of these atoms. So when you look at the group number, okay, when you look at the group number, it's going to tell you, okay, so the group number tells you the amount, sorry, it's kind of sloppy, the amount of valence electrons. Okay, so that group number is going to tell you how many valence electrons that you have. All right, so group 1, from hydrogen down to francium, all have the exact same number of valence electrons. Group 1 has 1. Okay, so group 1, let's just put group number in valence, VE for valence electron number. Okay, so group number, group 1 has 1. Group 2, group 2,
at this time, please release all students of the buses. Thank you.
Group 2, from beryllium down to radium, they have 2. So group 2 has 2 valence electrons. You're going to skip the transition metals. So we're going to skip group 3 through 12. Okay, so it's going to be 1, 2, skip a few, skip 3 through 12. Most of them are 1 or 2, and then there's a few oddballs in there. But so we're going to group 1, group 2, skip these. We're going to go to group 13. Group 13 has 3. All right, and we'll draw the Bohr model so that you can see it only has 3. Group 13 has 3. Group 14, from carbon down to lead, has 4. So then means group 15 has 5, group 16 is 6, group 17 is 7, and group 18 is 8. Okay, remember we said up here there can only be 8 valence electrons. So group 18, the noble gases, their valence level is completely full. No more valence electrons can fit. That's why the noble gases are inert, what we call inert gases. They do not react with other elements. Okay? Right, so let's look at another model. And actually you can see right here, before we turn the page, we did lithium and sodium. If we look at the last energy level, lithium has 1